Linear algebra is the language of data. Data is naturally matrix shaped. See, in the modern digital landscape, data isn't just stored in tables, it is mathematically defined by its arrangement. This matrix shaped nature of data allows computers to apply mathematical operations to real world concepts. Let us look at some examples to get a feel of it, like how data is naturally matrix shaped. Let us try to understand it. So if we talk about student marks, so we can represent student marks in the form of a matrix. So rows will be the students and columns will be the subjects. Like student 1, maths, physics, chemistry. So columns will be the subject, subject 1, subject 2, subject 3, and rows will be the student. So we can represent the student marks in the form of matrix. Similarly, if we talk about images, the pixel matrix, the pixel intensity matrix is a matrix representation of an image. If I talk about Netflix recommendations, we can represent Netflix recommendations using something called as user item matrix. User item matrix. We can represent neural networks in the form of weight matrices, and social networks we can represent using something called as graph adjacency matrices. So now it's very clear that data is naturally matrix shaped. Any sort of problem you talk about, you can represent it in the form of matrix. Now all these we can discuss in some more detail. If I talk about student performance, which is a tabular data. So we already saw that. So here the problem is managing and comparing academic performance of thousands of students across multiple subjects. Just imagine we are considering a college containing thousands of students. So now the problem is to manage and compare academic performance of thousands of students across multiple subjects. And here the matrix can solve the problem. So we can have a M cross N matrix where rows represent the individual students and the column represents the subject. And what advantage we get if we use this matrix to find the average grade for a subject, perform an operation on the column vector. To find a student's GPA, operate on a row vector. So in this matrix, the row vector will give us the performance of a particular student, and the column vector will give us the performance of the entire college for a particular subject. So that can be a very powerful tool. Similarly, if we talk about digital images, the visual data, now the problem is computers, they don't see shapes, they can read numbers. Because computers, if you talk about, they can only understand numbers, they cannot see shapes and all. So we need a way to represent images in the form of numbers, and we have pixel matrix, pixel intensity matrix. So a grayscale image is a single matrix with pixel intensities 0 to 255. A color image is a 3D tensor. So it is a stacked matrix. So we will be having a 3D tensor, a 3 stacked matrices for red, green, and blue. So now it's very clear that we can represent a image in the form of a matrix. If it is a grayscale image, one matrix is enough. And if it is a color image, we have to use a 3D tensor. So 3 matrices we stack on top of it. Like we have a matrix for the red, for the green, and for the blue. And why it works? Applying a filter like in Instagram or Photoshop is mathematically multiplying the image matrix by a smaller kernel matrix. So now with this image matrix, we can perform operations on it. To process the image, we should process the matrix. So if we talk about Netflix recommendation or Amazon recommendation, we have user preference data. Now the problem is predicting what a user will like based on the past behavior and some other factors. Now if we make use of a massive user item matrix where rows are the users and columns are the items. It can be movies for Netflix or products for Amazon. Now, how this user item matrix can play a role in predicting what a user will like. So, this user item matrix is a sparse matrix. Like in this, most cells are empty. So, AI uses matrix factorization to fill in the blanks, identifying hidden patterns. We call it the latent factors, like prefers sci-fi movie, like science fiction movie, or 90s nostalgia. So if we represent the user preference data in the form of a matrix, like a user item matrix, then we can perform some matrix factorization, which can enable us to identify hidden patterns, the latent factors, using which we can recommend movies or the products to the users. So now we are getting a realization like linear algebra is the language of data. Like how if we represent the data in the form of matrix, we can make use of linear algebra to solve problems. Similarly, if we talk about neural networks, intelligence data. So in neural networks, the problem is how does a machine store the relationship between an input and an output? Because see, the idea is that in neural network, it is a supervised learning. In neural network, what we do is that we know both the input and the output. We know both the input and the output. We give input to the neural network and it learns the pattern. So neural network, what it does is that it learns the relationship between the input and the output. It predicts the unknown function which can transform our input to an output. So in neural network, we know both the input and the output. Neural network learns the relationship. Now the problem is how it will store the relationship. So to store the relationship, if we make use of the matrix, like the weight matrix, every connection between neurons in a model has a numerical weight. So if we assign a, so we know that every connection among the neurons has got a weight, a numerical weight. And if we store that weight in something called as weight matrix, our problem will be solved. And let us see how our problem will be solved. So see, processing information is essentially a long chain of matrix multiplications. This is why GPUs are so vital. They are built to multiply matrices incredibly fast. So if we represent the relationships in the form of weight matrix, then computation will be very efficient because GPUs, they are made for to carry out matrix multiplications, to carry out billions of operations simultaneously. And that is possible. And this is the reason, like if we talk about deep learning or the deep neural networks, there the weight matrix can be very big. But with GPU, we can for carry out billions of simultaneous operations. And this is where linear algebra is playing the role in neural networks. Social networks. So social networks, we are dealing with the connection data. Now the problem is mapping billions of relationships like the friends, followers, likes to see how information spreads. Now if this relationship we represent it in the form of an adjacency matrix, like if user A follows user B, cell A comma B is 1, otherwise it is 0. So that's the concept of adjacency matrix. So if we make use of the adjacency matrix to map the relationship then what benefit we will get? Squaring the matrix tells you who is a friend of a friend. It turns sociology into a problem of graph theory and linear algebra. So the idea is that with matrix, if we represent the connection data of a social network in the form of an adjacency matrix, then using linear algebra, we can carry out certain interesting operations. We can square that adjacency matrix to get who is a friend of a friend. So we can turn sociology into a problem of graph theory and linear algebra. So now it's very clear that data is naturally matrix shaped. So if we represent the data in the form of a matrix, we can get some special benefits that we saw. So the key insight that we can take away from all this discussion we did, modern data problems are matrix problems. The modern data problems we are dealing with are basically the matrix problems. We no longer treat data as isolated snippet of information. By viewing the data as a matrix, we gain the ability to use linear transformations. We can rotate, scale, and project that data to find features that are otherwise invisible. If you can turn a problem into a matrix, you can solve it with a computer. So if we are talking about computation, if we are talking about GPU, then we have to treat the data as a matrix and not as a isolated snippet of information. If we can turn a problem into a matrix, we can solve it efficiently using a computer or a GPU. So modern data problems are matrix problems, and hence, if there is a matrix, there will be linear algebra. So we can say that modern data problems are problems of linear algebra.